This next paper that we are going to see here is the paper which is about machine learning in production. It's a survey paper from the colleagues in Erlangen, from Jörg Franke and his lab. The survey, the review paper style is reflected also in the number of authors that we have here. The main author is Andreas Mayr, and he has teamed up with Dominik Kißkalt, Moritz Benjamin Lutz, Franziska Schäfer, Reinhardt Seidel, Andreas Selmaier, Jonathan Fuchs, Maximilian Metzner, Andreas Blank, and the leader of the lab is my colleague Jörg Franke. The paper is entitled Machine Learning in Production, Potentials, Challenges, and Exemplary Applications. Thank you.
Hello everyone, my name is Andreas Mayr and I'm a scientific assistant at the Institute for Factory Automation and Production Systems of the University of Erlangen-Nuremberg. On behalf of my colleagues involved, I will now talk about a recent paper called Machine Learning in Production, Potentials, Challenges and Exemplary Applications. While recent trends like autonomous driving, natural language processing, service robotics or Industry 4.0 are mainly based on the tremendous progress made in the field of machine learning. The revolutionary aspect of Industry 4.0 is the possibility of interconnecting technical systems in real time, so the data obtained in this way can then be analyzed and evaluated using machine learning techniques, aiming for improvements in terms of quality, lead time, costs, or flexibility. However, as broad as the subject area of machine learning is, as diverse are the possible application scenarios in production. Especially for small and medium-sized companies, a systematic unification and implementation guideline for the adoption of economically viable machine learning use cases are still missing. In particular, there is still a lack of a structured overview of concrete industry-specific best practices that can be easily transferred to one's own production. Thus, this paper is dedicated to give a structured overview of exemplary machine learning use cases across different processes and subsectors of the manufacturing industry. Well, in this presentation, as well as the underlying paper, we will start with an overview of relevant notions, basic potentials and main challenges of machine learning. Then, exemplary applications of machine learning in production are given from a process and an industry sector perspective. The process point of view mainly covers the main manufacturing process groups of DIN 8580, such as primary, shaping, forming, or cutting. In addition, handling operations according to VDI 2860 as well as selected cross-process approaches are covered. From an industry sector perspective, application scenarios from various subsectors such as the production of electronics, electric motors or medical devices are outlined, and finally, we conclude with an outlook on future research and recommendations for actions are given. Well, so what is machine learning actually? Machine learning is a branch of artificial intelligence giving computers the ability to learn without being explicitly programmed. So, in general, a distinction is made between supervised, unsupervised, and reinforcement learning. In supervised learning, the machine learning model is trained based on a data set consisting of pairs of inputs and outputs, so-called features and labels. So, supervised learning aims to find patterns within the training data that can be used, for example, for predicting product quality based on production data. In unsupervised learning, the computer also learns from data, but without previously known output data. So instead, the algorithm learns, for example, what typical sensor data of a machine looks like in order to be able to detect future anomalies. And in reinforcement learning, finally, a so-called agent is ought to take actions in an environment so as to maximize some notion of reward. Depending on the learning type, numerous algorithms can be applied. For example, artificial neural networks, convolutional neural networks, support vector machines, or random forests. So, as powerful as machine learning is, as extensive are the possible applications in production. So when it comes to predictive maintenance, for example, machine learning algorithms can estimate the condition of machines or tools and predict the optimal time for maintenance or tool changes. In quality management, machine learning-based models can be used to monitor or even predict the quality of the product based on process data. Applying machine learning in process control is expected to result in a higher adaptability to changing conditions, stabilizing output quality and reducing reject rates. Especially in the field of robotics, machine learning-based object recognition and motion planning have recently resulted in major advances. Other exemplary fields of applications include the job shop, scheduling, fault diagnostics, and energy management. A comprehensive categorization, however, of machine learning application cases in production is not yet known, and neither the aim of this concise overview presentation. Similar to Industry 4.0 use cases, machine learning potentials can be derived from technological opportunities, also called opportunity push, or an existing need for optimization, also called problem pull. Methods like value stream mapping, Ishikawa diagrams, process capability analysis, or expert talks can all support the identification of relevant use cases. So, in the next step, the selected use cases need to be concretized and analyzed concerning the cost-benefit ratio. For machine learning projects, the data availability and quality strongly influences this analysis, as extra sensors, data storages, and processing capacities require additional investments. And based on this, the prioritization and choice of the most relevant use cases can be conducted, for example, via a portfolio matrix. For the project execution, the iterative CRISP-DM cycle with its 6 phases represents the most established method. In the business understanding phase, the problem and the goals of the project are analyzed, understood, and specified in a project plan. The second phase, the data understanding, addresses the analysis of available data to gain first insights concerning the machine learning goals. So data availability and quality represent a crucial requirement for even being able to apply machine learning. However, especially the connectivity of all planes still represents a major challenge. The subsequent data preparation phase consists of cleaning, transforming, and formatting the available data. With up to 70%, the data preparation is usually the most time-consuming part of a machine learning project. In the modeling and evaluation phases, these algorithms are trained and evaluated. So when choosing an algorithm, its robustness, that is to say, its response to unexpected situations, as well as interpretability, play a major role. In case of a successful implementation, the project is documented and finally deployed in the real-world environment. So, irrespective of the industry, production systems usually comprise a selection of manufacturing processes in accordance with DIN 8580 and handling operations as defined in VDI 2860. While the underlying paper provides a comprehensive overview of machine learning approaches at process and industry level from institutes worldwide, the presentation focuses on a selection of machine learning use cases, mainly stemming from our institute. So let's go to the first use case shown here. According to DIN 8580, cutting describes processes in which a form is altered by means of reducing material cohesion. In this context, machining seems to be the most important subgroup. Typical applications of machine learning applied to machining include predictive maintenance, tool condition monitoring, predictive quality assessment, and monitoring of abnormal process behavior such as rattle. Kißkalt, for example, detect anomalies like chattering using unsupervised burning and the non-negative matrix factorization method for dimensionality reduction. In addition, they demonstrate the capability for estimating the operational state solely based on the structure-borne sound without a permanent interface to the machine's control. For this, a modular system architecture for a data-driven monitoring system following the requirements of Industry 4.0 is proposed, as shown in the figure here on the right-hand side. So the second use case shown here. In accordance with VDI 2860, handling is a part of material flow and principle defined as the realization, defined change, or temporary maintaining of a specified 3D arrangement of geometrical bodies in a reference coordinate system. So far, a lot of machine learning applications address the autonomous planning and optimization of trajectories for articulated robot arms, as well as sensor data processing, for example, for 6D pose estimation. So in this context, for example, Blank et al. Present a pipeline combining so-called convolutional neural networks and template matching methods for 6D pose estimation. Blank's approach is especially suited for textureless industrial components. So in doing so, the convolutional neural networks helps to significantly reduce false positive pose estimations through a prior segmentation. The third use case shown here lies in the electronics production. The electronics production, the surface mount technology is widely used and thus requires extremely high yields and stable processes. The SMD assembly generally comprises 3 processing steps: solar paste printing, component placement, and soldering. So after each of these steps, additional inspection systems can control the process stability and identify faulty modules. As can be seen on this figure, machine learning can be applied for diverse use cases along the process chain. For example, since stencil cleaning highly influences the quality of printed circuit boards, machine learning can be applied to determine the right cleaning cycle. In the subsequent optical inspection, for example, solder joint images could be classified by convolutional neural networks. So the fourth use case shown here lies in the electric motor production. The electric motor production is confronted with increasing requirements due to electric mobility. Thus, the acquisition and intelligent analysis of process data promises great potential for tomorrow's electric motor production. So far, most of the existing machine learning approaches in electric motor production refer to the contacting process. The contacting process is particularly relevant for so-called hairpin windings used in the latest traction drives generation. So after assembling and twisting, the numerous contact points must be welded, for example, using a laser. To ensure a high quality of the whole winding, each individual weld seam has to be monitored for defects or other indicators of poor quality. So using machine learning, it is possible to assess the weld quality just based on images of the weld seam. Based on these images, defects such as holes and spatters or weld beads can be identified automatically. In addition, the electrical quality of the weld can also be assessed from this. Our first proof of concept at the Institute already showed good results, while we are still working to further improve the system. So the last use case is the X-ray tube assembly. The X-ray tube assembly underlies high quality requirements as it plays a vital role in a large number of medical applications. Well, unfortunately, the component for radiation generation in the X-ray tube can only be tested to full extent when assembled. Therefore, errors detected in this final inspection can be caused by a combination of variances in different upstream processes. In order to analyze the cause-effect relation on product quality, it is thus not sufficient to consider individual parameters in isolation. Instead, quality-critical parameters have to be analyzed across processes. In this context, Selmaier et al. Present an approach for the efficient cross-process analysis of product quality based on the standardized procedure which maps the well-known CRISP-M cycle to the RAMI 4.0 architecture. Well, as can be seen from the exemplary applications, machine learning holds great potential in production. The process perspective mainly covers the manufacturing processes such as cutting, handling operations, and cross-process approaches. On the industry level, exemplary machine learning use cases in the production of electronics, electric motors, and medical devices are outlined. Although the structured overview is anything but complete, it is already a good basis to identify own use cases from an opportunity push perspective. However, most of the approaches mentioned here are still subject of research and not yet ready for practical use or even widespread. So this is the reason why research on the application of machine learning must be further promoted and the necessary data be provided by industrial partners. As always, it is important to simply get started in order to avoid falling behind in the long run. Well, the listed reference can also be found in this paper. Thank you very much for listening.
Thank you very much to the colleagues in Erlangen for that presentation. We're now switching over to the live call with Andreas Mayr. We have a phone connection with him established, which we are trying to get live just right now. Yeah. Hi to Erlangen from Berlin. Can you hear us?
We can hear you.
Okay, thank you. That goes clear and well. Thanks for the presentation. Thanks for handing in the article and doing like the intensive review work. As we know from the FABS colleagues, you're really experts in the electronics markets and electronics production, and we really appreciated the paper also in this topic. what I was interested in is the electronics sector has always been ahead of other industries in regard of data and production data and usage of production data. Now that you see these machine learning things in there, do you also think they are ahead of other industries, or how do you think this correlates with each other?
Well, I think the reason for being electronics production so advanced in comparison to other industry is that we have a very high degree of automation in electronics production. And always when you have something automated, you also have data to evaluate. So that is the reason why electronics production, and especially semiconductor production, is very ahead of that in using machine learning. For example, electric motor production, it's also a mechatronic product, but here you see that we still have some challenges because of the manual work we have here. So only industries like semiconductor or electronics productions have a lot of data you can already use. Other industries like electric motor production are very handling intensive, so that you are not really able to evaluate, to analyze some kind of big data.
Yeah. Okay. Thank you. So the applications of the machine learning that you have cited and reviewed in your paper, would you estimate that the ecosystem of these tools and applications, will it be more into the broad sense, or will it go into in-depth, or will it aggregate to one aggregated tool set, or how did you observe that? How heterogeneous is this world that you have been into?
Well, as I already said, at the moment we don't have like a fully automated production chain in a lot of industries. So one has to look at one or two manufacturing steps. And that is the reason why we don't have like a huge ecosystem right now. We just have to focus on single steps and to evaluate how one can really use artificial intelligence in that step. Because in a lot of steps, maybe artificial intelligence doesn't make sense. There are like more sophisticated methods of statistics you could apply, but no artificial intelligence. So it really depends on. And when you have a look at the application scenario of handling, here you see that there's a difference between using machine learning in robotics or using machine learning in analyzing some data from machining processes. So it really depends on the application case.
Okay, thanks. That was a very clear statement. Thank you. Thank you for joining us in that question and answer session. Thanks for putting all the effort in the paper, and all the best for your future work. See you then. Goodbye.
Goodbye.
So this was the paper, Machine Learning in Production, Potentials, Challenges and Exemplary Applications, made by the colleagues from Erlangen.